Okay, good morning. Let's get started. So, pass the homework assignment to the front, and the solutions to the homework assignment and the handouts are on this corner, right? Couple of clarifications. Even though I give you a answer key, I'm not expecting you to exactly follow what I said, right? Throughout this class, I strongly encourage you to think of how you might solve it. So if you come up with a solution which sort of makes sense, and if you can explain it, that's perfectly fine. So you don't have to exactly follow what is given. That's one suggestion. That's one like a straightforward way of answering it, but you're free to tweak it, say it in a different fashion. And if the TA takes away points for you saying it in a different fashion, let me know, because I told the TAs that they're not to take away points for answers which are unconventional but make sense, right? And for the exam, one clarification: the option where I said you can do it on Friday and have people do a take home applies to both. I mean, applies to all the students. It's not just for CPEX or whatever, right? But as of now, as of this morning, I have 8 people who wanted to do it on 25th, Monday, and 5 who wants to do it on the Friday and do a take home, right? So unless some people want to strongly ask to keep it on Friday, I would like to move it to Monday, right? To me, it doesn't matter either way, but we can't do it both ways. I mean, I can't do it on Friday and Monday, right? So, yeah, in general, if you have a genuine reason why you can't be on an exam on a particular day, let me know, and we can work something out. Essentially, I would like you to, I mean, I would like you to take it in the class, but if you have to take it away elsewhere, you would still follow the same rules. You still have the 15 minutes. So if you take it on a take-home, does not mean that you have the whole week, right? So this is one of the catch with the take-home exams. I'm sure you guys have taken take-homes before. So if you have a take-home exam where the time is unbounded, like basically 2 days, then I have to make questions which will take you 2 days to answer, right? So exam questions always grow to fill the available time, right? So if you ask for a take-home exam which will take you a month, then I have to come up with a question which will take you 1 month to answer, right? So it's in your best interest to keep it at 50 minutes, not to make it stronger, right? You're probably aware of that, but the same goes for open book, open notes too, right? I think if you have open book, open notes exam, you hardly ever need the book. I've never seen a faculty who would ask an open book question, what's on page 4, paragraph 3 or something, because it sounds too straightforward, right? So anyway, so that's the thing. So if you want to change it to back 21st or something, let me know. But as of now, I'm going to move it to 25th, right? Make sense? Are there any other questions of what we're looking at so far? So what do you think of this whole synchronization stuff? Does it sound easy? Is it confusing? It's kind of sort of in there. One of the problems with the operating system, which I hope to convey in the classes, it depends on a whole bunch of other stuff that you probably learned in other classes, but it's not explicitly, maybe you didn't think about it before or what have you, right? One of the stuff is the role of what compilers will do. Maybe you didn't take a course in compiler, but at least when you write a program in C, right, what happens to that program? What gets known to the operating system? What should the compiler do? What should your program do? What should go to the kernel or compiler, the operating system? And what should be held by the hardware? What shouldn't be held by the hardware? Is sort of what we are trying to worry about here, right? And so we kind of draw on some of the stuff that you probably did. So when you wrote programs, all the stuff I'm talking about, synchronization, right, or atomic transactions, if it was available to your programming language, this is something that you might have used it. You may not have used it, but this is all going back to your knowledge of what you know about programming and all these things. So it's trying to tie these things together. And unfortunately for this topic, the whole serializability concept, I think it's a very beautiful concept, right? It's a very beautiful concept because it lets multiple threads run in parallel, but still give some guarantees, right? It does not give guarantee that thread 1 will run and then thread 2 will run. It says either thread 1 will run and then thread 2, or thread 2 will run and then thread 2. But even relaxes that. It says We can run them in parallel, but it'll look as if one of them ran before the other one, right? So this guarantee lets the system be fast while still allowing you to make write programs. And when you think of writing a complicated thread program, you have to keep track of all these things going. You have to imagine what happens in all these threads. Having this notion tells you something about what to expect, so it cuts down on the amount of program debugging you have to do, right? So in this case, right, this is what it appears like, right? But this is what the actual machine ran like, right? Where those two reads and writes could be in parallel, right? So essentially, it could run at 6 instruction cycle, but the guarantee it gives you is it will appear like it ran like this, right? And that's just a powerful way. So unless you get the guarantee, you cannot really program, because then you have to program all the logic in here. If you can give the guarantee, that's good, right? So atomic transactions, notion of serializability and conflict serializability is a very powerful concept. You have lots of papers on this. This is you can do a thesis on just one aspect of this, a PhD thesis kind of stuff. So I'm trying to squish all of them into 1 or 2 lectures, right? And if you take a database course, this is essentially what they're trying to achieve, right? Without this, there's no database. Without this, databases are just a bunch of query languages and stuff. Query languages are trivial. What really goes underneath is this notion of how do you make sure that you have these transactions that are fast but have some sort of predictability, right? And so we'll continue with the notion of serializability and how you might implement this, how you might implement some of this stuff. And this notion of two-phase locks is again a database concept. So one way to achieve these things is the notion of a two-phase lock, where you go through a phase of achieving locks and then releasing locks, right? You don't let, so the notion here is, when you have a transaction, you say upfront what locks you want, or you acquire locks in a certain fashion, and which is you always acquire first and then you start to release, right? If you do that, then you can prove that that transaction is conflict serializable, right? And the proof is beyond the scope of what the class will look into. But the notion, if you can do something like that, and we'll see again this two-phase lock in another context, right? Which is, it does not guarantee deadlocks, which is the next section we'll look at. So some of these mechanisms will allow you to get the concept of conflict serializability without the full atomic transaction, right? And again, the full explanation of how the proof is way beyond the scope of what we can look at. Another way to implement this is the notion of a timestamp-based algorithm, right? So the timestamp-based algorithm says that you timestamp every transaction operation with some time, right? It could be the physical time on the system. It could be logical time. We haven't talked about logical time, so we'll ignore that. So it could be physical time, right? So this means that if you have 2 transactions which are in parallel, each operation of transaction, you have to put the time, right? You have to put the time it was created. And then we define a protocol such that you can tell which of the transactions can move forward, which of them have to be rolled back, right? So to do that, we have the notion that for each transaction, you'll have a time that the timestamp of this transaction I, which is the time at which transaction Ti took place. That's the transaction time. We also have a notion of when the last successful read or write on a shared item was. So this says this is the time when a successful read. So this is the time when a successful write happened on that item, right? So you're trying to, so there are multiple times, right? So multiple transactions. So we are trying to look at each data item and see if that data item, what was the last successful write operation or read operation on that. And depending on the time difference between the transaction and what was done there, you may have to roll back or roll forward. And that's the algorithm, right? Essentially, this way, everything is time-stamped. So if it violates some principle, we'll see what those are, you'll have to roll back. If it doesn't violate, then you make the system move forward, in which case you make the write or the read timestamp go forward, right? So that's the notion. So every transaction, every operation is timestamped with the current time, and you also keep track of when is the last time the data item was modified, right? So suppose you have, so the two, I know these turned into squares, but suppose you have a transaction item, right, TI, which is trying to do a read on Q, right? So this is going back to something like this, right? There you have a read of A or what have you, right? So suppose you have one transaction, like this transaction, and it's trying to do a read of A, and in this case we're talking about read of Q, right? If the transaction time, the current time that it's trying to do is less than when it was last returned, right? Because remember, one of the things you can do in the logs is you can go back and forth. So when the transaction tries to operate on this data item at time ti, and if it looks like the last person who successfully wrote into it was in the future, that means you're playing back the log, right? That means this cannot happen, right? You cannot read an item which is in the future. Does that make sense? Remember, the logs can be rolled back and forth, right? So you have a data item. You try to see who was the last one who successfully wrote into the data item. And then you're trying to replay a transaction, right? And the transaction says that I want to read something at time 1. And time is increasing, right? And you look and you see that somebody wrote this item at time 2. Because you're just playing back. So somebody wrote it at time 2. Which means that you cannot read that variable, right? Which means that you're trying to read something which hasn't happened yet, right? So if you go back here, so if that read B on the read B, it's reading this, right? If that read B is trying to read this write B, right? Then the time that the last one successfully wrote B would be this time, right? But it's trying to read it at that time, and time is going forward as you go down the board, right? So you can't let that happen. So that means that read is trying to happen right here. Does that make sense? You're trying to see how you can interleave these things, right? So if this write had succeeded, then the read can only have happened before, and since it didn't happen, it has to be rolled back. So you check to see if the write has succeeded from a future time, in which case this transaction should be rolled back. Otherwise, if it is in the past, that means this particular operation can go forward, right? This is because you're trying to read something which was returned before your current time. That means you can make it go forward, and then you increase the last time someone successfully read. So you have the write timestamp. So you update the last time someone successfully read something from that variable to the current time of the timestamp. Right? Does that make sense? So that way you guarantee that a transaction, if you replay, it will not violate the notion that the previous transaction, if somebody wrote it, you're not going to read some object which is not returned yet, even though you're playing back and forward the logs. So this defines an order in which reads can happen. This defines that you cannot read something in the future by somebody else, right? And you have the similar concern for write. If you're trying to write something, you have to make sure that nobody else has read the value, right? If I'm trying to write some value and then somebody has read it, somebody has read this value before, then that transaction would have to be rolled back, because you can't write something which would have affected somebody else, right? So you have two conditions here. One, to make sure that nobody else has read the whole value, and nobody else, the write conflict, right? So essentially, these whole things. So if you have all these notions, it defines you an order which states that certain operations cannot happen because they are violating the conflict serializability. So once you have these transactions, you can be guaranteed that it's conflict serializable, right? I suggest that you think about this in more detail, and this is not expected to be a simple concept. This is expected to be pretty hard concepts, because of the nature of what these things do. But those are something that you will have to worry about if you want to write programs. When you try to use programs with multiple threads and stuff, you need to have some sort of a guarantee, right? You don't want to have enough guarantee that the whole system is completely predictable, where every operation happens one after the other, sort of like what you do for a uniprocessor. Because if you do that, you don't get good performance. You want some level of unpredictability, but you can't completely let these things go and say, I have no idea what happens. I just let them run, right? If you have all the threads doing whatever they want without any sort of guarantees, writing a program or proving the program will do something that you can sanely assume is very hard. And some of the notions you have to go through with this is have this notion of which order things can happen, which order things cannot happen. And that particular order that you allow is part of the notion of a conflict serializability. Right? Does that make sense? I think it'll probably make sense if you go back and read the textbook to make sure that you kind of follow along what it's trying to do. But the goal here is to make sure that only one order is possible, the other order is not possible, right? So if you go back to if you look through the stuff, this particular transaction would go through, right? And for doing that, you have to make sure that the blue read, right, and then the orange read, you have to make sure that they happen in that order. If the transaction was replayed the other way, then the orange blue B read B could happen before the blue read B, and that will be prevented by the rollbacks we talked about, right? So this particular one can be done. That if you try to do the other way, you'll have rollbacks. You'll ensure that this will happen. So in order to put these things into context, I mean, all the stuff we talked about is in the context of database systems, and the whole concept came from database system, right? How might this be implemented on an operating system, right? The book does not talk about this. The book talks about this as this notion of atomic transactions and commits and all those things. But how would you implement this, right? Let's see how you might implement this. Suppose we have a system called begin transaction, abort transaction, or commit transaction. And let's say you have something like this, right? This is I wrote a program where it says begin transaction, and I say commit transaction. And within the section, I modify something. I say buff of 10 equals star PTR plus plus, right? So here I'm modifying the buffer value, buffer of 10 with this value. So I'm writing into that buffer of 10, right? I'm reading from PTR, star PTR. So I'm doing a read of star PTR, write of buff, and then I'm incrementing PTR. So I'm doing a PTR plus plus, right? So there is one read, two modifies, right? And some test, I mean, whatever the test is, and this abort, right? When you do abort, with the transaction model, you expect all the things that you did to be undone, right? So you expect buffer of 10 to become whatever the value was before you came into this code segment, right? We don't know what that is, but buffer of 10 has to go back to the value it had before this assignment happened, right? That's the notion of a transaction, right? Right? Can this work like this? Which is what you wanted. I mean, you would like to be able to program these things like that, right? What is the catch in making this happen? So think of this. So should this be done? So what should the operating system do? What should the compiler do? And anyone want to take a guess? It's going to be a guess because it's not in the book, right? So this is something that we are kind of pondering. So in the conceptually we talked about creating transaction records, right? So we talked about creating records which say buff of 10, old value, new value, and PTR, old value, new value, and so on and so forth, right? who writes those records? Obviously not you as a programmer, because I didn't say anything about those, right? Should this be done by the compiler, or can the operating system decide what you're doing? So when you call this abort, can operating system take you back to the state of the system while you are at begin transaction? Anyone wants to make a stab at it? This goes back to one of the questions we had in the, I think, the last exam, right? When does the operating system get control of system to do anything, right? Here you, like when you're doing this buff of 10 equals star PTR, you want somebody to log those things. You want somebody to keep track of those. Can the operating system do that?
No, because it only gets to run when you get interrupted. So if you're running, then it's not running.
Yeah, the operating system is not running, right? I mean, when you're doing this, the assignment operation, you are running in your application space. Operating system is not running, right? So even if it wanted to, it can't know that you're saving all the stuff, right? So it's not clear who should do it, right? I mean, that's one of the reasons why you don't see it on your programming languages yet. It's not clear who should do it because you expect sort of the compiler to do it, but compiler gets very tricky, right? So compiler will have to say, when I'm creating this code, it has to keep these logs. So it has to know that it's running on a log-based system. It has to tell the operating system everything. So it has to have a very tight collaboration between the application and the operating system, telling it to log all the stuff. You don't want to log all the time. You want to log only when you're inside these transaction stuff, right? The other catch is, what happens when you do abort? What do you expect you should happen to your thing? When you abort a transaction, right? We said things should be going back to the way where they were, right? What happens to the thread? Should it just die, or should it go back to that begin transaction, right? And I don't think the answer is clear, right? When you abort a transaction, like the examples we give you in terms of if you're moving some money from checking account to savings account and all those database kind of stuff, it sort of makes sense because in the database sense, if you're moving money from your checking to savings account, things aborted, then you have to move the money back kind of stuff. But in the program concept, if this thread was to abort, do you exit the thread? Do you go back to the begin transaction state? Or what have you? It's not clear. So when you as a programmer want to use some of these concepts, you will have to know a lot more about these things than you probably want to know. And as a programmer, you have to know that when you do a abort transaction, things may happen and you have to recover from those, right? And it's not clear how normal users would react to that, right? Imagine you as a programmer, right? So if this happens, it sounds beautiful that all the effects of the buffer is gone when you do abort, right? But what are you supposed to do as a program? You can't just exit the program. You have to, I mean, you could, but you would like to make progress. So you have to know how to recover from an aborted transaction and what to do. And those kind of stuff makes this system extremely hard, right? There's been some work done on this concept. The way they do that is something we haven't looked at yet, which is the notion of memory pages, right? So the way we can implement this in operating system, we'll see this in the next module, is to have protection on memory pages such that when you start a transaction, you make all the pages no access, right? And then every time somebody reads or writes, the hardware will send a message to the operating system. Then it can keep track of what is happening, right? And that sounds good, but it's extremely slow. That means every time you read or write anything, the operating system gets involved. And it does not know what you're doing. All it can do is it can save the whole page and write it back, right? And that's just not, that makes the system so slow that no one would want to use that, right? So even though you would like this concept, it's still not at the stage where you can go ahead and program these things into your program. We kind of stuck with the notion of the locks and semaphores and stuff we talked about. Not this higher level constructs of transactions and stuff. But people are working hard on bringing these stuff because this will hopefully make this programming model a lot easier than having to worry about it the way you guys have to do for the homework project, right? Worrying about locks and semaphores and all those things. It's easy for simple programs, but when you start to look at a big program, it can get very hairy, right? So if any of you get to go on a summer internship this semester or something, and if you look at some of the real programs that people are working on, right, they don't have much of a choice. They have to use threads, right? Unless you don't want to use all the processing capabilities available. But once you use threads, you have to worry about all these concepts, whether you like it or not. And the challenge is, it's not as hard, but you have to understand exactly what's going on, because otherwise you can make mistakes that you didn't intend to, right? So I want to wrap up with the notion of a atomic transaction with that, because from what you learned from the book, it seems like it's a very easy thing to move the database concepts into the operating system. I don't think it's that easy. I think you need the support of the programming languages. I think you need to change the way people think about programs and stuff, and that may or may not be as trivial, right? Right. So this is a fairly long chapter. So we looked at a number of different ways of achieving critical section and the different functionality we need, especially because when you have multiple threads operating on the same data, you have to protect them, and you need to have these primitives to give you critical section protection, right? So next, in the next chapter, we'll look at the notion of a deadlock, right? So deadlock happens because we have the notion of critical sections. So when you have critical sections, and we say only one thread can go through a certain resource, you run into another problem called deadlock, and we have to figure out how to solve them, right? So the notion of deadlock is when you get into a state where no progress is possible at all, right? And that may be because I need the CPU, you need the CPU, and you have the CPU, and till you get some resources you cannot complete, and till I get the resource I cannot complete. So we get into a state where neither of us can make progress, and we'll see what conditions those happen and how you may avoid them or how you may prevent yourself from that state, right? And again, this is an artifact of having the multiple threads and locking mechanisms. So, and some of the examples, so if you have a semaphore, right? If you have a semaphore, if you have, let's say, binary semaphore, and A and B, and if two threads were to call them as this order, right? Wait A, wait B, wait A, wait B, and wait B, wait A, right? So if both of them happen sort of in parallel, and thread 0 got the wait A, right? And thread B is in wait B, right? So it wants to get the next one, but it can't because they're both waiting for the other one. So they're both holding one, waiting for the other one. And if it's a binary semaphore, then there's no way they can finish. So you get a state where no progress is being made, but no progress can ever be made unless somebody gives up. And in this context, nobody can give up, so we kind of stuck in the state, right? It happens in other states too, right? So if you are operating on devices which are exclusively usable, like for example your printer, right? So if you wrote a program which needs a printer and a CD player or something, right? So if you have one of those and it has a CD and it's waiting for a printer, and something else has a printer waiting for a CD, they're both kind of stuck, and you can get into this state, right? So that's the notion of deadlock, and we'll see how it happens and stuff. And before we do that, we'll define what some of the parameters for this stuff, right? One is the notion of a resource, right? We have to have a notion of resource, which is why you get a deadlock, because you wait for resources. So you, as application, you need resources. Can be CPU, can be semaphores, or what have you. So those are some of the resources that you operate on, and you can assume that there are certain instances of a resource. If you think of a processor, if you're on a multiprocessor system, you have that many resources, right? So that's a little bit more realistic case where you have not only one of those, but you have many of those, right? The assumption here is any one of them is good enough. So if you're waiting on a processor, and you're running on a processor machine with let's say 4 processors, the assumption is any one of them is good enough for you to do the job. You don't need a particular processor. You can use any of the processors to get your job done. So So that's the notion of resources and instances of the resource. They all have to be replaceable with each other, right? And the way we assume people would use these systems is you'll acquire the resource, do something with it, and then you release it, right? Because if you may release it when you exit the program or what have you, but essentially you have to acquire the resource before you can write into or modify something or read something, and then you release it, right? And again, these are the definitions of the system. For deadlock to happen, 4 conditions have to be true, and those are important conditions, and those are the takeaway message from this particular chapter, right? You have to have 4 conditions which have to happen, and if one of them doesn't happen, then you may not get into deadlock, right? The first notion is the resource that you're operating on has to be mutual. It has to have the mutual exclusion policy, right? Which is sort of like the critical section. It says that only one thread may be using the resource at any one time, right? If you have a resource which could be shared by any number of processes or threads, you don't have mutual exclusion, right? So if you have for example, if you have a printer and only one person can be printing on a printer at any one time, which is a reasonable expectation, right? So you can't have multiple processors writing on the printer because it's of the nature of the device. So if you have resources which only one can use at any one time, you may run into deadlocks. So printer is one example, and your locks and unlock is one example. Critical section is one example. Critical section is one area where you only want one thread to be inside the critical section. So that means that something could get into a deadlock condition. The other condition is all these systems, you have to have the processors or threads holding on to resources and then wanting more, right? You cannot have a problem, you cannot have deadlock if I don't have any resources. If I'm waiting for one more resource, then I cannot get into a deadlock because I don't have a resource, right? So that means I may starve, but I don't cause any problem to anybody. I have no resource. I may be wanting this printer, right? And because of somebody's deadlock, I may never get this printer, but I'm not going to cause a deadlock because I don't have anything that I can create a problem with, right? And the other condition is preemption is not allowed. Even though you have mutual exclusion, I'm not allowed to take resources from you, right? So you have to hold a resource, and that resource cannot be taken away from you. You have to give it back, right? So if you have a resource where only one person can use it, and you have processes which hold one of those and want more, right? And you have the condition where resources cannot be taken away from you in a forceful fashion. And the last condition is you have to have a circular wait. Circular wait, it does not have to be a single circular wait. It may be that process 0 is waiting on some resource which is being held by process 1, which is waiting on some resource, and which is waiting on some other resource, and so on. But if you can kind of follow along all this route and you come up to a point where it's a circular wait, you get into deadlock, right? So you can think of the dynamic philosopher problem, right? If you think of dynamic philosopher problem and you assume that in that problem, right, the fork or the chopstick is not shareable, right? I mean, only one philosopher can use a fork at any one time, and they need 2 of them, right? It's not like they can eat with one of them, so they need 2 of them. So they have to hold one and then hold the other to eat, right? So if you wrote a program where they took, so let's say the left fork, right? If all the philosophers took a left fork, that means all of them have a left fork and they're waiting for the right fork, right? So it's mutually exclusion because only one of them can have the fork at any one time. All of them have one fork waiting for another one, right? All of them, you cannot, I mean, the philosophers are not allowed to stab the next philosopher and take the fork from them. So they have to wait for the stuff. There's no preemption here. And the last one is you can kind of follow along, right? So you say philosopher 1 has this left fork waiting for the right one, and then this and the next one and the next one and the next one and the next one. So you find that if they kind of get into the state, all of them are waiting for the other one. They have holding on to one. That means they get into deadlock, right? That means there's no progress. No progress can ever be made unless you do something drastic to break the condition. So if all the 4 conditions are happening in the system, and it will happen when each of them have their left fork, the system is in a deadlock state where no progress is being made. They're still following all the notions of critical section we talked about, right? But this is this goes beyond that because of the notion of a critical section mutual exclusion principle. You can get into this problem, right? And that's the notion of deadlock, and that's an important problem to worry about because when you get into the deadlock, your system just sits there, right? You can make no progress. If this happens to your PowerPoint or what have you, your PowerPoint just sits there. You can't do anything else, right? If the philosophers are doing this and they're sitting there, somebody has to come out and say, somebody has to change it, right? You cannot change it with the way the algorithm is running, right? You can only change it in a way that the philosopher problem becomes different, right? So you can either change it where the philosophers kind of stab the next philosopher, takes the fork from them, or they put the fork back or what have you. You have to break one of these conditions. If all these conditions are happening and they get to the state where all of them have their left fork, you will run into deadlock, and there's nothing you can do about it, right? And unless you can get rid of one of these conditions. Does that make sense? So these conditions are very important. These 4 conditions. Yes.
So then why wouldn't most operating systems use preemption just to get rid of this problem?
So we'll get to that in a little bit. There are some resources which can be preempted, some which cannot be preempted, right? So in terms of like let's say a printer, right? So if you had a printer, we'll see a little bit in a couple of slides. But if you have a printer, right? Preemption would mean that, let's say you have printed half your document. Preemption would mean that I have to kill you, right? I have to take the printer away from you, which is not a bad thing. But the next one may continue, but you have to rerun all the stuff you did, right? Most of it don't do a transaction. This is one case where you like a transaction, where you can kind of replay all the stuff. But otherwise, your program made some progress. It's, let's say you're printing all the records, all the grade records for all the students, right? If you come like halfway through and you took the printer away, you have to start all over again from the beginning. But the application would not do that. It does not know how to do that. So you can't do the preemption, right? So if you get into deadlock, that's what you have to do, which is you have to preempt by killing a process, right? And you hope things will work out. But it's a messy thing, right? Because these resources are not preemptible, right? There are resources which are preemptible, like your keyboard, right? Can be shared. I can take the keyboard, give it to another process, and come back. You're fine. Printer kind of things you cannot preempt. Printer, tapes, and CD burners and all those things. Those are exclusively non-preemptible, right? Again, it depends on what kind of resource you're using, right? So the way to understand, to visualize how these things are happening is through a notion of a resource allocation graph, right? So you kind of draw how the system is behaving using the resource allocation graph. The essentials are you have a notion of processes or threads which want resources, and you have threads, right? And each resources can be multiple instances, and you draw these graph vertices as follows. If a process, which could be a thread, is requesting some resource, you have an arrow going from process to request, right? If you have an arrow going from resource to process, that means this resource was allocated to this process, right? And you can use this to sort of see how the system is behaving. So for example, this is one case of a resource allocation graph, right? So you have one resource where there are 2 instances. You have one resource where there's 1 instance. And you have 3 processes and 4 resources, right? No one wants this resource. And the idea here is, if you want resource R2, either one of those dots are fine. You're not asking a specific resource. Any one of them is fine, right? So in this case, right, P3 has the resource R3. P2 has resource R1 allocated to it, right? And so P2 has resources R1 and R2 allocated to it. This is one of R1 allocated to P2, and P2 is waiting for P3, right? And P1 has one of R2, it's waiting for R1. Does that make sense? So this is one way to visualize this stuff, how the system is behaving, to see if you are in a deadlock condition, right? So what you do is you try to see if there's a way to get it to a circular wait by looking at the system, right? So if you follow the arrows, right, So if you follow this arrow, you can follow from here, goes there, goes there, goes there, but there's no arrow coming back, right? So there's no circular weight in the resource allocation graph. So this particular state is safe. This particular state is safe because it's not in deadlock, because there's no circular weight, right? It does not say how long it will take for you to progress, right? So for example, P1 may not make progress for a while because P1 is waiting for resource R1, which is allocated to P2, right? And P2 is waiting for R3, which is allocated to P3, right? So in this system, if P1 wants to finish, it has to be the case that P3 will have to finish. When it finishes, it will release the resource R3, which will be given to P2. And hopefully, if P2 does not want anything more, then eventually P2 will finish and it will release R2 and R1, in which case P1 can complete. Does that make sense? That's the way you would see how the system will proceed, right? We don't know how long it will take, but we know for P1 to finish, P3 has to finish, because only if P3 finishes, it will release that resource 3, which will have to be needed by P2, and once P2 finishes, they can release resources that can make progress, right? So we're not talking about starvation, we're not talking about how long P1 will finish, but we know that eventually, if all these applications eventually finish, then P1 will start a deadlock, so they can make progress, albeit slowly, right? So if you change it to this state, right, where P3 now waits, the only change is P3 now waits for R2, right? It's not waiting for any one of these dots. It doesn't matter, you can take any one of those. But if you follow it along, this state is this is a deadlock state, right? Even though there are two resources, you have actually two circles, right? You have the you have to follow through the discussion, but essentially what happens is, so for P3 to finish, it needs one of R2, right? And for one of R2 to be released, either P1 has to finish or P2 has to finish, right? So only when P1 or P2 finishes would they release one resource that can be used by P3, right? But P2 cannot progress because it wants R3, which can only be released if P3 finishes, right? And P1 cannot finish it because it's waiting for R1, and R1 is being used by P2, and P2 is waiting for R3, and R3 is being given by P3, right? So even though there are multiple resources here, you cannot make progress at this point, right? Yeah, again, you're assuming all the conditions. You're assuming that it can be it's mutual exclusion. You're assuming that it's not preemptible, and so on and so forth. But if you follow this graph, you notice that there's a circular weight. So even if you have two resources, you still have circular weight which cannot be solved. So if a system ever gets into this state, it's in a deadlock state. It cannot make progress. It's dead. Okay? But just because it has circular weight does not mean it has to be safe. It has to be unsafe, right? So if you change it to this model, where there is a circular weight, right? It looks like P1 is waiting for, R2 is allocated to P1, but P1 is waiting for R1. P3 is waiting for R2, right? So it looks like there's a circular weight, right? But it's not unsafe, because even though there's a weight here, because you have multiple resources, the system can still succeed, because P4 has a resource, right? It has a copy of resource 2, and same P2 has a copy of resource 1, right? So if P4 and P2 eventually finish, they will release this resource, which could be used by P1 or P3 to get out of the system, of the deadlock, right? So even though there is a circular weight here, it's not deadlock state, because there exists one way to solve the problem. The way is, if P4 finishes, then it will release this resource, in which case it can be given to P1, in which case P1 can finish. If the release is released, then P3 will be satisfied. So P3 will release the R1, which can be satisfied by P1, and so on, right? So you have to do analysis on, so you have to create a resource allocation graph to see if there's any possible way of getting out of the system. You have to use graph theory algorithms to figure out if there's a way out. If there's a way out, you're not in deadlock. If there's no way, then you're in deadlock condition, right? So resource allocation graph are a good way. So the basic facts are, if there are no cycles, there are no deadlocks. If there are cycles and there are multiple processes, you either may be in a deadlock or may not be in a deadlock, depending on how these things play out, right? And as you have more resources, it becomes a little bit more complicated, right? Because you have to look for all possible cases where that resource can be freed. If you have only one instance of a resource for the whole system, then if you see a cycle on the resource allocation graph, you're in a deadlock, right? So that brings up to some of the issues that you brought up. So once you know that there's a notion of deadlock, right, what can you do about it, right? Some of the ways is you can make sure that the system will never ever get into a deadlock state, right? And we'll see some of those mechanisms. So you make sure that system will never ever get into deadlock state, which means that you make sure that the 4 conditions do not simultaneously happen, right? You can make sure that of that by saying one of the conditions will never happen, right? And some of the systems can deal with that. So that's one way, which the operating system can say, whatever you do, you can never get into a deadlock. The other one is you try to avoid deadlocks. You try to do your best to avoid deadlocks. But if deadlocks happen, you try to recover from it, right? Or the third approach where you don't pretend that deadlocks ever happen. So you just move along fine, right? Most operating systems will follow the third path, which is they pretend that deadlocks never happen. If deadlock happens, you just reboot the machine, right? Many of you may have seen deadlocks, right? You may have seen deadlocks where a process is kind of stuck, right, on something, right? A pop pointer, something is stuck, and there's nothing you can do. You can't kill the process. You can't get out of the system. The only thing you have to do is reboot kind of stuff, right? You may get into a state for a number of reasons, because I can't precisely say that's because you're deadlocked, right? Why do you think I can't say you got into the state because you are deadlocked? Because the operating system does not keep track of it, right? It's up to your program, you as a programmer, to see if it deadlocks, right? You might run into this case when you do this program, right? You may run into deadlock, which means that nothing is happening. If your program suddenly stops and does nothing else, then you probably got into deadlock, and it's up to you to figure out what is happening, right? So the first notion is we try to see how we can prevent deadlocks, right? How we can prevent deadlocks. The way to prevent deadlocks is to make sure that those conditions cannot happen, right? So the first condition is the mutual exclusion, right? Mutual exclusion says that a resource can only be used by one process. How do you make sure that that is not an issue, right? So I said printers are one case. Printers is a case where the printer device is mutually, it can only be used by one process. How do you make sure that printer hardware device, even though it can only be used by one process, can be shared by multiple users at the same time? Many of you have used printers, right? How do you make sure that when you're writing something into a printer, how does your machine make sure that 2 processes can print to the same printer? Which many of you may have used it, right? So you go into, let's say you go to Word, you're trying to print something, and you go into IE, and then you try to print something, right? You never run into a case where it says, printer is busy, come back, right? Do you know what happens when you try to print here? Yeah, you spool it, right? So essentially what you create is another data structure where all the print jobs come to this. So you don't really print to the printer, you print it to this buffer, right? So that way you can create this multiple copies essentially by saying there's only one printer. You have a printer job whose job is to send this stuff. It collects all the print stuff, and then once it's done, it sends it off to the printer, right? And that's why you don't run into a problem where even though there are multiple processes, they can continue to print to the printer because they're all printing to different stuff, right? And the print queue may print it after you're done with all this stuff, right? It may work with some things, it may not work with something else, but that's one way, right? So for some resources, even though only one person can be using it at any one time, you kind of fudge it by creating another buffer and writing into it, and then hoping, to do a 2-step process, right? It works for printers, it may work for something else, right? I'm going to stop at that we are kind of out of time. But essentially, I want to think about these things. I mean, deadlocks is an important problem. Most operating systems just give up their hand, but we'll see why they don't want to attempt it in the next lecture.